Hi and good afternoon. My name is Jonathan Bailey. I'm editor of Health Estate Journal, the IHEAM monthly magazine. Welcome to today's CPD accredited webinar held by Kohler Interruptible Power in association with HEJ. Today, healthcare engineers looking to get a better understanding of UPS systems in medical environments can learn about the latest guidance on the subject from Alex Ems, who is Technical Director at Kohler Uninterruptible Power. The session will cover the fundamentals of designing a UPS system, enabling healthcare engineers to explore the various UPS options available to meet their requirements. Since with medical IT systems, as Kohler UP puts it, there is no standard one-size-fits-all solution. Alex Ems, Technical Director at Kohler Uninterruptible Power, has over 30 years experience of the UK power protection business with 19 years service at KUP. He started out as a field service engineer, progressing to senior engineer, supervisor, service manager, operations director, and now technical director. If you have any questions as the webinar progresses, please type them into the panel on the right of your screen, and at the end of his presentation, Alex will answer as many of the questions as time allows. I'm sure you'll find this an informative and valuable session. All attendees at today's webinar will also receive a follow-up survey, which Kohler UP would be grateful if they could complete. Over to you for your presentation, Alex.
Excellent. Thank you very much, Jonathan. And welcome everyone. We get a lot of people coming on, which is great to see. So as Jonathan was saying, my name is Alex Ems. I've been in the industry for quite a long time. We concentrate now on trying to train and help people understand how we install UPSs. So very welcome questions as we go. But for today, I will turn off my camera for the presentation, and we'll come back on later on for the questions. Okay, so you don't want to look at me the whole time we're going through. So we are going to cover today various things. I'm going to do a very brief overview of Kohler and KUP. We're going to look at the requirements for UPS in healthcare, look at the fundamental types of UPSs, the differences between transformer-based and transformerless. Get a lot of questions around dual sources, isolation transformers, around fault clearance, different things. There's different requirements for batteries in healthcare scenarios. So we're going to look through those various parts, and we do tend to try and cover a lot. There is a lot to cover here, but I say the questions are always great. So KUP, who are we? Kohler Uninterruptible Power, formed originally in 1997 as Uninterruptible Power Suppliers Limited. Personally, I joined the company in 2000, and we were bringing in the first transformerless modular UPS into UK and Ireland. The company was acquired by Kohler in 2008. Very good for us. Allowed us to expand, opening offices in Singapore, acquiring a company we worked with in Ireland, Pure Power, and then we renamed as Kohler Uninterruptible Power back in 2019, part of the Kohler Energy Group as it was then. Last year we were stood off as a separate business, as Kohler Energy transferred over, and now that's what we are today. So we have a lot of experience. We've got over 100 UK employees, thousands of units employed across the countries, good employee engagement, and for customer satisfaction, we're top 10 in our marketplace. And our first time fixed rate, our service side of things is something that we're really dedicated to, and currently running well over 95% on first time fixed rate, which is a measure of the quality of our people and our products. So we have expertise and customers in all types of applications. So this, what we're talking today is just one thing. Healthcare, hospitals is just one area where UPSs are required. Nowadays, UPSs are put everywhere, from all kinds of things. It's gone away from just a data center computer market to the things like retail and telecoms and transportation, absolutely everything is reliant on power now, and you know, we are able to fortunately offer UPSs for all those applications. So the UPS for healthcare, what's the requirements? We have some standards, obviously, BS 7671. We have section 56 about safety services and 710 medical locations. And of course, we have the guidance of HTM 0601. And in that guidance, we're going to go through a lot around that guidance and what it means when it comes to the UPS part. And of course, we have to consider the business continuity and the risks to patients. So the business continuity, as you probably know, from 4 to 1, 1 being the most critical, where it's medical support services. And we have the risk of to the patient from E up to A, which is the life support complex surgery. So the HTM gives us some guidance of where UPSs should be used, as does BS 7671. And in this guidance, it lets us know where the maximum interruption time is 0 to 0.5. Now that's actually quite a big gap, 0 to 0.5 seconds, because many computers won't run with a 0.5 second gap. So we're looking at 0 for many, many applications now. And to do that, you must have a UPS online in circuit with that kind of situation. So this is typically where we're going to have it in medical IT sections for risk gradings A, you know, and B. So this is where we're going to typically have that UPS application. But there are lots of other applications where we have UPSs for lighting and for admin and everything else in the healthcare sector. But we're going to be typically looking where we need to back up the medical theatres and recovery areas, etc., like that. So with the UPS fundamentals, HTM talks about 2 types of UPS, a double conversion UPS and a single conversion UPS. Now the double conversion UPS should be classified as BFI SS 111 under the standards. And it should have a rectifier, an inverter, a battery, a bypass, and a maintenance bypass switch. And that's laid out like this. So typically the mains comes in here, and it is typically at 1 or 2 supplies. And if it's 1 supply, we just link it out. Power comes in through the rectifier, through the inverter, through the stack switch, and out to the load. We have a static bypass available if there's a problem or we need to bypass it. And ideally a maintenance bypass, so we can bypass as necessary with that. So with a single conversion UPS, a VI or a VFD, these are offline UPSs. So what happens here is you have the mains, it's keeping the battery charged but not running on that, and that's normal. It's not running on inverter. It's typically running on this line, on mains out to the load, until the mains goes out of tolerance, and then the inverter switches on and feeds the load. So these are offline UPSs. Sometimes people refer to them as kicking in when it's required, but these are typically the small UPSs underneath the desks and things like that that you see, short autonomies. Okay, typically don't have a maintenance bypass and typically only can have a single source into them. Okay, so not generally used for life safety, but used in other applications within healthcare. Okay, the battery, like I said, is typically short and internal, doesn't tend to meet the requirements of HTM. So UPSs over the last 20-25 years have changed quite a lot. Traditionally, we had this transformer-based UPS where we had a rectifier, an inverter, and a transformer. The transformer was there because we couldn't produce the required voltage without it. Modern UPSs now, it's not just us, it's most manufacturers are making transformerless UPSs. So this is where we have an inverter feeding directly out to the load without a transformer in the output. Loads of advantages to transformerless UPSs. They're smaller, lighter, critically much more efficient than the old transformer based ones. So it has made some difference in the way we need to operate, and we have to do that. We understand that, and HTM understands that as well. But when we're looking at static UPSs, there are three typically main types of architecture that we look at. We have a standalone UPS. This is where we have one rectifier, one inverter, one bypass, one control. Or we have a true modular. Okay, a true modular is when every module is a true UPS. So it has a rectifier, a bypass, an inverter, a control, a bypass. There's nothing duplicated in a true modular UPS. And then you're going to get something in between. It could be a semi-modular UPS that has maybe a rectifier inverter modules, but the common parts which are shared are the bypass, the control, the display, and things like that. So some are duplicated, some is shared. So it's just understanding the differences. The main difference with the semi-modular to the modular is typically a bypass. So a semi-modular will have one bypass only, whereas a true modular will have distributed bypass to give redundancy on the bypasses as well. So what are we going to protect against? It's regulated by EN 62040. So we have just if mains failures, circuits and surges, if you can have a little break, it's an offline VFD UPS. If you want to protect against under and over voltages, we have a VI UPS, a voltage independent. But to protect against everything, switching transients, power surges, frequency variation, harmonic, we need an online double conversion VFI UPS. Okay, and this is classified, as I said, 62040. So the volts frequency independent VFI. So whatever happens to the volts and frequency on the input, the output voltage and frequency stays within limits. The SS means it's always going to be a sine wave in normal or on inverter, and the tolerance 111 means we will never lose the output voltage for any period of time. It will always stay within tolerances. It's typically within plus or minus 15–20% of the mains. Actually, the UPS will be much better than that, but that's the tolerance for within the standard. Okay, so that's the basics. What we do find a lot of questions around is dual supplies and requirements of HTM 0601. Okay, so it suggests that the rectifier and bypass may have a common supply connection. The ideal connection should provide separate connections for the rectifier and bypass line. Okay, so when we look at a UPS, we typically have a supply, and if it's a single source, we link out the rectifier and the bypass, so we have a single source. If we want it to be dual feed, we take out these links and we feed another link, another supply on to the bypass supply. Okay, so it doesn't necessarily have to have it. It depends how we're going to do it. Okay, and this is very much the difference between a central UPS and a final circuit. Okay, what's worth noting is it doesn't have to be from a separate supply. It doesn't have to say that. It actually, when it comes to a central UPS, you don't need a separate supply. And if you have a modular UPS, like this case, we have one supply and we actually split it out inside, and it's protected with fuses between the rectifier and the bypass anyway. So we're actually giving it a dual source supply inside. So what many people look at is these drawings in HTM, these diagrams and examples. And it talks about single conversion UPSs for final circuits. Okay, and people look at this drawing and we see the UPS here and here feeding the final circuits, in this case the medical IT, the IPS. Okay, and they see the UPS is fed from two different sources. Okay, but that's because the medical IT needs two sources. Yeah, not necessarily the UPS. The final circuit needs two sources. Okay, so this is a final circuit UPS with dual source supply for those final circuits. Okay. When we look at another example, this is where we have central UPSs feeding multiple medical IT IPS systems. Okay, so now we have a UPS here and a UPS here. Okay, each UPS is fed from one main supply. Okay, in here. All right, the outputs from each UPS feed up into the ATS, the automatic transfer switch in the medical IT IPS system, to be able to transfer from one UPS to another if one supply was to be not available. Okay, so we can use ATS in here. The UPS has one supply, but we have got two UPSs, so therefore we have dual supply to those final circuits. Okay, and that's critical to understand the difference, okay, between a final circuit and central. So we need dual supply at the final circuit. So if you just have one UPS, one IT, then you need dual supply of that. But when we're using central UPSs and each one is feeding all the medical IT, then that is the dual supply because we've got two UPSs. Okay. So in this example, in the final circuits chapter, it does show a final circuit UPS with an ATS feeding a medical IT IPS circuit out to the theatres, which are interleaves on the output. Doesn't actually show where the ATS is. Is it here? Is it on the medical IT? Is it upstream? It doesn't really give that example, but you know, we can decide how we need to do that for best. Okay. So in HTM, it suggests the use of isolation transformers. We've talked about the dual supplies, and that is one reason for having isolation transformers. But another main reason is because of four-pole changeover. And we're going to look through the different scenarios. But what we have to be critical here is we understand the two applications of a transformer. Okay? Because it does say, where for resilience purposes, UPSs are fed from different PES transformers, the UPS may experience neutral referencing problem. Okay? So it recognizes that modern UPSs have a four-wire connection on a rectifier and a four-wire connection on bypass, which is for modern UPSs. Older UPSs, let's say 20 years ago, would have a three-wire rectifier and a four-wire bypass, different, okay? So when we got four-wire rectifier and four-wire bypass, if we was to connect that from two different transformers, we would be connecting the neutral together, and that would not be good, so therefore we need a transformer to isolate. So what we're saying is that an old transformer-based UPS would only have a three-wire rectifier. The bypass would have the neutral, and that went all the way through the UPS, not connected anywhere else, out to the load. Okay, so that's no problem. With a modern UPS, we have a four-wire rectifier and a four-wire bypass, and that neutral is linked inside. Okay, so if we have different supplies, we will link that neutral, and that is an issue. So for dual feed with an old type of UPS, we have a supply transformer, PES here, free wire to the rectifier, no problem. The PES on supply 2 on the bypass supplies the neutral for the UPS, for the load, for the bypass, and it goes out that way. Okay. So we're not connecting different neutrals together in a traditional way. Okay, and this is many UPSs fitted many years ago were like this. Okay, nowadays our UPSs have four-wire connection on the rectifier and a four-wire connection on a bypass. So we need to put a transformer in place so we don't connect the neutrals together from the PES. Okay, so we're having this, and this is reference to this neutral. Okay, so we don't have an issue. It is not a galvanic isolation. We're not re-earthing it at this point. Okay, and that is the big difference. We're isolating the two supplies. So this is common. This is common for many modern UPSs, and we have to be aware of this. And this is what HTM is warning us about. That, you know, we have these two different sources. We have to be careful. Okay, but there are ways to overcome this. Okay, now the second need for an isolation transformer is quite a primary one for this, is where we use 4-pole changeover devices in the upstream distribution to the UPS. Okay, HTM says, you know, that neutral earth reference will be lost for the period of the changeover. This risk of unstable output will depend on the load. The more unbalanced, the higher the risk. And the optimum solution is to provide a dedicated 0 phase shift transformer on the UPS. Okay. Well, the UPS will not become unstable just because we lose a neutral earth reference. If we lose 3 phase and neutral on the input of the UPS, the output of the UPS will remain fine, stable, 230 volts line to neutral, 400 volts line to line, but we have got no neutral earth reference. So the neutral earth will be floating. Okay. A 0 phase shift transformer is optimum, and because it creates no phase shift between input and output, and it means we can put a bypass around it if we need to. A normal isolation transformer will have a 30 degrees phase shift. Okay, so what we're worried about is not this one on the left. This is a healthy one, and the neutral is connected all the way through to the earth. Okay, so line to neutral is 230, line to line 400. Okay, neutral earth 30. On the right, we have a distributed neutral floating. This is where the neutral is broken with reference to the supply transformer, a distributed neutral. Okay, this is obviously a dangerous situation, and so the voltage between line and neutral could raise to anything. Line to line will remain 400, but the problem here, it is dangerous. Okay, and this is one type of floating neutral, but it's not the floating neutral that we're trying to overcome. Okay, we are trying to overcome the problem of a 4-pole changeover. Okay, and this is where we have a 4-pole changeover on one supply, typically over to a second supply being the generator. It could be 2 mains transformers that we're switching between. Okay, and we are worried that we're going to lose that neutral earth for that period of time. Okay, so the HTM suggests that we should have an isolation transformer either on the input to the whole UPS, input supplied to the bypass, the maintenance bypass, or on the output. And it talks about item C on the output of the UPS is the optimum option, although it comes with added cost and may impose on available space. Okay, it makes no difference. The cost is the cost. If you have a transformer on the UPS, it's going to add a cost. Sometimes actually putting on the output could be cheaper because we can have a smaller one. Okay, and of course it does impose space, but it doesn't matter if you put it on the input, output, whatever, it still takes up space. Okay, but it's worth having a talk with the supplier of what's optimum. Okay, having it on the output is a good solution for various reasons, and we can have a look at it. So what we do get a lot of confusion around is that many people think an old traditional transformer based UPS, because it's got a transformer on it, has this galvanic isolation of the load. It creates a new neutral earth, but it doesn't. So when we look inside a transformer based UPS, we have a rectifier, inverter, a transformer here, and the output transformer star point is connected to the input neutral of the UPS, not to earth, because we're using this neutral to reference the output and we're referencing it with the bypass. Okay, so we cannot just connect this to earth, because therefore we would have a connection to earth at the source and we'd have a connection in the UPS to sources, but we cannot do that. So it doesn't matter what type of UPS we have, it does not create the new neutral earth. If it's a transformer or transformerless, we still need that output transformer to create a new neutral earth. Okay, so we have to put a transformer, ideally as it says, on the output. 3-phase in, typically a delta star transformer, and we re-earth the neutral on the output to create a permanent neutral to the load, so we never lose that neutral earth on the load. Okay, so this is an old transformer-based UPS, and a modern one would be very much the same here. So we've got no transformer here, but we have to put one on the output. Okay, so it doesn't matter if it's transformer or transformers, you need an isolation transformer to re-earth that neutral supply. All right, so when it's on the output, we do have to make sure it's rated for the output of the UPS or whatever protection we have. It is possible to put up small isolation transformers spread around the property, so we have one big UPS and small transformers fed to local load, so we don't have to be in the same place. So I mean, it's worth having a discussion about how we're going to do this. So if we have dual source and we want galvanic isolation, we want to create new neutral earth, how do we do that? Okay, so what we're going to be doing is, if it was an old transformer-based UPS, we would have two sources, one for the rectifier, one for the bypass, and an isolation transformer to create the output reference on the neutral. Okay. On a modern transformerless UPS, which most people are using, if you want to have that UPS with two PES supplies, we have to put an isolation transformer in to separate the neutral, and we have to put an isolation transformer on the output to create a new neutral earth. Okay, that is an option. Okay, to use two PES, but what you have to think of is, do I need to put two supplies into it? Okay, because quite often these UPSs nowadays are being used as a central UPS, and we only have one supply into it. Okay, we feed the medical IT from two different UPSs. Each UPS has one supply. Okay, so that is critical to understand from day one. Okay, we are seeing lots of designs where people say the UPS must be fed from two supplies, and then we're feeding the medical IT from two different UPSs, and then we value engineer it and say, well, no, we just feed the single UPS from a single source, but each UPS is fed from a different PES. Okay, but an alternative, if you want to have the UPS with two supplies, is to use an ATS on the input. Okay, so put an ATS here from the two different supplies. Lots of advantages to doing this. A, you don't need a transformer, and B, what a lot of people don't realize is, if you lose one supply to the rectifier, a lot of people think it will transfer to the bypass, but it doesn't. The UPS will run on battery until the batteries run out, and then it will transfer to the bypass. In this solution, if we lose a supply, the UPS will go on battery for a short period of time, the ATS will change over, and then that new supply will be feeding the UPS, everything goes back to normal. So a good, resilient application is to, if you want two supplies, is to use via ATS in this way. But it depends where you want the dual supply. Do you want it at final circuit, or do you want it at central UPSs? Okay. So the UPS will have the ATS for the changeover for the dual supplies, and the galvanic isolation transformer to recreate the neutral earth, as you would on any type of UPS from any supplier. All right. Okay. Lot to get through. So we are now looking about for clearance on UPSs, for health systems, for life safety systems. It's all the same. We are having critical supplies here. So how does the UPS actually react to this? Now, we have the main supply, and typically the UPS, an online static UPS, the load is running through the rectifier, producing a voltage which we connect to a battery, and then we convert the DC back to AC and feed the load in that manner. Okay, when we're on battery, we feed through this way. Okay, so the UPS sees a short circuit, and it has a couple of different capabilities. The inverter itself is very limited. We're making the voltage up using transistors, IGBTs, so we might have a capability of 2.5 times the nominal current for maybe 100 milliseconds. Different manufacturers, different models will have different capabilities. It tends to vary from 2 times IN to 3 times IN for around 40 to a couple of hundred milliseconds. Okay, but it's not defined. It's something that you have to check with each UPS model. Okay, the bypass though has a different clearance capability. It's effectively mains, so we'll be switched it to mains. We might have 10 IN for 10, 20, 40 milliseconds or so, a much higher capability. So most UPSs react very similarly. Okay, we have a capability of running an overload up to 150%, and above that it tends to treat it as a short circuit. Now the difference is in an overload means we can produce the correct voltage, supply that overload at the correct voltage for a period of time. It's limited, but it's a period of time. Whereas a short circuit means we can only supply a certain amount of current, and we limit the current by limiting the voltage. All right. So if the fault is under 150%, we can treat it as an overload. We start the timer. It's an exponential timer, but most UPSs can do 150% for 30 seconds to a minute. And we try and use that to clear the fault. And if not, if it does, it's great. We go back to normal, say it's had an overload. But if not, we treat it as a short circuit. And the first thing the UPS will say is the bypass available? Have I got mains? Is it available? Because if it is, it will transfer the load to the bypass, okay, in about 3 or 4 milliseconds, extremely quickly. And we use the mains now to try and clear the fault. And if it clears the fault, great. Typically, the UPS will transfer itself back online. It will leave an alarm up to say it's had a short circuit. But if it doesn't clear it, something's got to give. Okay, either fuses internally on the bypass or an upstream protection to the UPS. It's not ideal, obviously. We shouldn't design it like that, but that's what will happen. Okay, something has to give if we've got a short circuit. Okay, if the bypass is not available, we're in a mains fail situation. The inverter will go into short circuit current limits. Okay, so it will give the maximum current it can. Typically with hardly any volts, it's just pumping current at low voltage for a very short period of time. Try and use that to clear the faults. Okay, if it clears the fault, it comes out of current limit, goes back to normal, leaves an alarm. Okay, if not though, inverter will turn off in some form or fashion at some point, and that depends on the model, the make, things like that. But typically it will turn off at some point. Okay, to protect it itself as much as the load. All right. So if we look at the reg 7671, it says where a UPS is used, it shall be able to operate the distribution circuit protective devices and start those devices in emergency condition on inverter on battery. Okay. HTM effectively follows that. It gives you the reason why. UPSs have got a very limited short circuit, but basically it says you have to comply with 7671 and be able to operate the downstream protective devices with it. There's some things in there that are a little confusing. Any questions on that, you can speak to us, but mostly it's correct and says you have to operate the downstream devices. Basically, because if you have a fault here, you want to open this device to keep everything running. Yeah, we don't want, if you have a fault there, you don't want everything tripping. You don't want UPS going off. You want everything else still to run. So the device must trip. Okay. But it does say every output device needs to go. Okay. So if you have a short circuit here, what is the point of this actually tripping? Because if this trips, you lose everything. All right. So sometimes you might say, well, I don't need that to trip, or I might not even need that device at all. Okay. You do, however, if you have a central UPS feeding multiple circuits. Okay. If we have a fault here now, we need this to operate because we need this load to run. I mean, ideally, we shouldn't be having non-life safety loads and life safety loads on the same thing, but people do it. And if we have a short here, we do want to trip that breaker. Sub-main breakers get more difficult to trip than final circuit MCBs. We have to fully understand the UPS and the circuit breaker to make sure we can operate that breaker. Okay. Of course, if we have everything's life safety, we do see this a lot. We have a central UPS here, maybe a 200 kilowatt, 300 kilowatt, feeding multiple IT. We have to be able to operate these devices if there is a problem. Okay, so quite often we're seeing 50 amp devices here to feed 10 kVA IPS, and we need to operate these if there's an issue. Okay, it's not being done properly in a lot of places. Okay, and this is one of the reasons why we run these events. Okay, because we see a lot of things aren't right. So for safety services with a UPS, okay, now where we said is the bypass available, we cannot rely on that bypass being available, because it might be in an emergency situation where we have to clear the protective device on inverter, on battery, because there is no mains. So that means the inverter short circuit capability has to be used to clear the downstream device, okay, and do it. If it doesn't comply. Okay, it's as simple as that. Just because it turns off isn't a reason to say it's safe. Yeah, we have to clear the fault because we want to keep everything else running. Yeah. So when the UPS is online, we have an output short, and we need to clear those breakers in the required time, depending if it's a final circuit or sub main. Typically, we're tripping final circuit in 0.4 of a second. Okay, and we have to be able to start those loads as well. You know, typically in hospitals, everything's running, everything's fine. What we also see in a lot of life safety applications is we have to put the UPS on and then start up the load. Could be a lot of motor load, things like that, that we have to be able to start on the inverter when it's needed. Okay, so we have to make sure the UPS can do it. We should always use the smallest device downstream that we can, you know, first of all. Don't stick with the typical 32 amp type Cs, go for the smallest breaker. And we have to be very sure that the UPS can do it. We see an awful lot of incorrect sizing of UPS. It doesn't work on UPS as you would expect to trip circuit breakers. We are very confident. We've sorted all our UPSs out with circuit breakers on in our workshop. Fully understand how things work. I'm very confident we can trip circuit breakers. And if you come along with one we haven't tested, we're very happy to test that as well. We do have further information, like I say, on that. If you want to come to us, please do, and we can talk further on that. So, batteries in healthcare, there are some requirements in HTM. It talks about non-toxic gases emitted from battery. There are no special ventilation required. Batteries, although it's not toxic, hydrogen is emitted from the batteries, and we do have to vent it as required. Okay, so there are venting requirements. You cannot put a battery in a sealed room in a sealed place. Okay, so HTM tends to grow towards the 10-year valve regulated lead acid battery. It is a good option for a standby battery. 10-year doesn't cost a lot more than 5-year, but you should be specifying it, okay? And it has to comply with the requirements, okay? But it also specifies things like you cannot use push-ons. You know, it has to be a threaded insert type battery. So this typically means a larger battery, okay? And it should also be flame retardant, okay? And this is careful. You need to be careful with this, because if you just go to UPS manufacturer and say, I want a 20 kilowatt UPS for an hour, you might not necessarily get what you want, okay? You've got to say exactly what you need from the UPS and the battery. Now, one thing that HTM is quite clear on, you should keep the battery at 20 degrees, okay? It makes sure the battery performs correctly. We size the battery at a temperature, okay, typically 20 degrees, and that's for the autonomy. Because if it's below 20 degrees, it won't do the autonomy. Above 20 degrees, yes, it will do the autonomy well, but it will, the lifespan of that battery will be severely reduced, okay? So very important to condition the battery correctly for lots of reasons, all right? Talks about battery arrangements, making sure you can split the battery. Talks about battery string monitoring and alarms where appropriate. It talks about the split battery to minimize disruption. So what they're talking about is having multiple strings of batteries and some monitoring on it. This is more for resilience than maintenance, because typically we're not going to take off one string of batteries during operation, carry on running with reduced autonomy. That's typically not going to happen in a hospital environment. But if you have multiple strings of batteries, we have some resilience. If we do have a battery failure in one string, the other string will still be there to back it up. So it's much more of a resilience thing than a maintenance thing. All right. As I said, battery cell, battery string monitoring should be considered where appropriate. And it's often not done. It might be considered, but it's not done. But just for interest's sake, you know, there are systems around that we can monitor every single cell block in the system to make sure we know if it's going to work or not. Okay. But with a management system as well, we are seeing this in data centers, government places, things like that, because of the advantages, the massive advantages of being able to extend the life of the battery by managing the charge voltage of the blocks. Okay, on a large battery, it saves cost by putting a management system on from day one. This is different to a monitor. It's a management system that also monitors. Okay, but worth a consideration for UPS installations, especially on the larger installations. It's worth having a look at to improve the performance of the UPS, resilience of the UPS, and for the management system, make it last longer as well. Okay, so battery autonomy. This is where it talks about single conversion UPSs, not really designed for that life safety application. They typically don't meet the requirements that you want. There's normally short autonomy. The batteries are typically 5-year push-on type batteries. So fine for non-medical applications, but not really used for the life safety part of these things as well. So where we are using double conversion UPSs is typically 1 hour or 3 hour. Okay, 1 hour if we have a secondary power supply available within the 15 seconds in the form of another supply, a generator or another UPS. So that's typically what we have an hour. It's 3 hours if you haven't got anything else. So if it's just maybe a clinic with only one supply, no generator, then you need a 3-hour battery on the UPS. One thing that it doesn't talk about in HTM, but it should, is the fact that the battery should be sized for end of life. So if you size a battery for 1 hour at day one, as soon as it starts being used, it's going to age and you won't have an hour available at full load. Okay, the battery is considered to be end of life when it's got 80% of capacity. So that's not an hour, is it? You know, so we have to, well, you should be oversizing the battery to allow it to have an hour just before you change it at end of life. Okay, by doing that, we have to add on 125% from day one. Okay, well, add 25%. Okay, size it 125%. Again, not going to be done unless you specify it. All right. So the UPSs should be commissioned and validated. So this means that we will typically come back after commissioning. So we go to site, build the battery, commission the UPS, get it on charge, come back in a week's time with a load bank, put on the full load, turn the mains off, and prove it does the autonomy you require. For healthcare, this should be done. It's in the HTM and it should be done. Typically, this is an option. So again, you know, you have to specify that you want this, okay? Because it will be added onto the job and be done. So always worth doing to prove that the supplier has actually given you what you've actually asked for. But HTM is you know, it's a requirement. All right. So we've seen that UPSs and batteries need different needs. Typically, the UPS can operate in a variable temperature. They're typically 0 to 40. If we keep it as close to 20, 25, the better. They're sensitive to dust. We shouldn't be in a dirty, horrible environment. We should be in a clean environment. Okay. Everything's safe. You know, we're locked behind the door. Everything's okay. Typically in the weight of 100 kilos or upwards. And typically we put that in similar equipment. Now the battery needs to have a stable temperature for best for performance and for lifespan. Okay. There's a small amount of hydrogen coming out of it. It's not so dust sensitive, but we should still keep it in a good environment. But if we've got a big room like we're looking at here, we want to control that room. The battery voltages are dangerous, often best in a dedicated room, or we put it in a partition the room off for those batteries to be done. Okay, so we just have to consider the weight, the safety, temperature, a lot more considerations around the battery than a lot of people do. Okay, so getting towards the end, we got to look for what's the load, what quality of it we need from the UPS. We have to make sure we understand the difference between a kVA and a kilowatts. Most traditional UPSs used to be sized at 0.8 power factor. Okay, now it's variable. It might be 0.7 to 1. Okay, so you have to be very careful what you're asking for from your supplier. The central or final circuit UPS, this defines where the dual supply is required. We need dual supply at final circuit. Okay, that might mean having 2 central UPSs feeding those supplies. Okay, supply requirements. What's the rating? Is it dual? Is it single? What you're going to have? That's the supply to the UPS. And then the redundancy of the UPS. Are we going to have redundancy in the fact that we've got 2 central UPSs? We're going to have a centralized UPS with N+1 in it. That's all the kind of things you have to talk with the stakeholders about what type of redundancy you need. The autonomy of the battery is critical. We need to understand the regulations. We need to make sure we have the right type of battery, make sure it's sized for end of life, things like that. Batteries are the primary cause of UPS failures, typically because they're not looked after. People don't understand the state, they don't test them. So we need to, either put some redundancy in that battery. That's the best way of doing it, alongside monitoring and management of that battery. Often not considered when we're putting in a UPS. People don't talk about the battery, they talk about redundancy in the UPS and forget the battery. Okay. We have to make sure we design for installation and maintenance. We see some awful installations, but we should be designing that in, so we can, it's in the right environment, we can get to it for maintenance, all those kind of things. The size and weight of the UPS is often underestimated, and that location where it's going to go. This cannot go in a little cupboard underneath the stairs. This has to be a proper room for the UPS to allow maintenance, make sure the environment's controlled, things like that. And very importantly, we know the status of that UPS. We need to have it connected to a management system, BMS system or something like that, so we understand that the UPS is available when we need it. Okay. So hopefully today you realize specifying the UPS is critical. Okay. Specifying the power factor, the quality, the redundancy, the efficiency, all these things is very critical with the battery. And our battery at end of life at 20 degrees, separate batteries per module, redundant battery strings, all this stuff will get you a good system that you want. Okay, if you don't, you tend to get a bad system. It fulfills a poor spec in a poor way. Okay, so please, be very careful of what you're specifying and how you do it. Okay, so that's the end of the presentation. Slightly overrun, but hopefully not too bad. So how was that?
Thank you very much, Alex. Very interesting and very comprehensive. Having heard you speak on similar subjects before, yeah, you're always that's always your manner. We've had 1 or 2 questions. I would encourage listeners to carry on putting questions in the panel on the right-hand side of their screen if they have them.
Yes,
and obviously Alex will do his best to answer them. Alex, if I may go ahead with one or two of the questions.
yeah,
One
sure.
audience member said, I have a question regarding the battery isolation switches typically installed next to batteries. The gentleman says, based on site experience and issues, it seems these switches would be better placed outside the battery room. This would allow the batteries to be isolated during an incident such as a fire or discharge, as smoke and fumes might prevent the batteries from being disconnected. He says, have you had any issues with this, and how would you recommend this being put into the design, etc.?
Okay. Now, the isolation of the battery does two things. One, it allows isolation between the battery and the UPS. But one of the other big things is protecting the cable between the battery and the UPS. Okay. So it has to be physically as close to the battery as possible. That's for the protective side of the cable, because the battery is always live. Okay. Yeah, a good point that we might want to isolate it externally. In that case, we have to have protection of the battery and an isolator outside the room or next to the UPS. But we have to have both. Okay, so we can't just say, well, I'll put the battery in one room and the isolator protective device in another room. Typically, UPSs will actually stop the charge. If it sees a problem and you turn the UPS off, that will effectively disconnect the battery anyway. So if there's a fire, things like that, we're going to be switching off the UPS, which will disconnect the battery electrically anyway. So that's fine. Okay, hopefully that helps.
Sure it does. Somebody else has asked, are there any UPS systems with lithium-ion batteries, and does that comply with HTM 0601? With lithium, do you still have the same ventilation requirements? And how much more expensive would they be? The questioner said 2 times more expensive or more than that?
Typically, a lithium-ion battery hasn't got many advantages for the healthcare environment. The lithium-ion battery, the advantages it has is it can be discharged very rapidly, very efficiently. Okay, when we're talking in minutes. When we're talking hours, it doesn't have the same advantage that it does over the fast discharge. So it becomes actually not much smaller than a lead acid battery when we're talking about a 3-hour battery, and therefore it becomes much more expensive. Okay, it's a factor of I can't really give a factor because it does depend on lots of things. Autonomy is typically the big one. When we're going for like an hour, 3 hours, it may well be much more than 2 times the cost of a lead acid. The biggest problem we're experiencing at the moment is with a lithium-ion battery is insurance. Okay, we have a lot of customers asking for price for lithium-ion battery, which we can do, but always check with the insurance company first who's insuring that building, because we've had many people come back and say our insurance won't allow it. So go to the lead acid. But
is
the lead acid
is that due to fire risk or?
Yeah. So we have that. People say yes, you can have a lithium battery, but it has to be in a special enclosure or an enclosure out in a car park, you know, in a container, or you have to do a lot more fire rating around the battery to stop it spreading, things like that. Yeah, unfortunately we've all seen the effects of those lithium batteries. But to be honest, in a life safety application, the lead acid battery is a very good solution. It's a very good solution. It's quite efficient at that long, slow discharge that we're designing it for. So, yeah, there's no real need for that lithium in this solution.
Thank you. Somebody else has asked, does battery redundancy need added batteries or additional battery strings? They've also asked if the presentation recording will be shared to attendees later. The answer to the latter question is yes, but I wonder if you can answer the question about battery redundancy needing added batteries or additional battery strings.
Yeah, so battery redundancy, typically means you need additional strings. Now, it means, let's say we had a 100 amp hour battery, you could have that as a one single string, but you could split that to have two 50 amp hour strings. Okay, so that will give us redundancy, but not half the autonomy. It doesn't work linearly, but you would have some autonomy. Typically, it does depend on a few things. So what we will typically want to do is understand, with the redundancy, do you want to have the option of losing a battery and still have full autonomy, or if you lose a battery, do you want some autonomy? Okay. Typically, due to cost, people will say, well, just make sure I have some autonomy so I can get the generator on and things like that. So we are typically taking the battery or amp hour we want and splitting it across multiple strings and ensuring that the UPS can still give a bit of autonomy on the remaining strings once we've taken one out. Yeah.
Thank you. Another question. If the UPS has a single output connection, why do we need to put a protective device in the output if the UPS performs that function itself?
Yeah, good question. You don't have to. What we do find is that people have to put a big UPS in to be able to clear the downstream protective devices, and then want to put a small cable in just to feed the load. In that case, you have to protect the cable. Okay, so it's a balancing act. It's a real balancing act. You know, we do have one output, and if we're feeding that onto a distribution board, feed it with the correctly sized cable, and then from the distribution board downwards, we want to be able to trip whichever device is in that board. Okay, so yeah, it's just that balancing act of what's the best for a single solution. As we said at the beginning, there is no common answer. We have to design each solution independently. But yeah, it's a good point. Don't put a protective device if you don't need to, because we have to trip it. Yeah.
Thank you. Had a good range of questions today. Another listener has said, in the galvanic isolation slides, you showed options for either an extra isolation transformer or an ATS, automatic switchover. What are the benefits of using an ATS? Is it cheaper?
Okay. First of all, there is the ATS or isolation transformer is so you can have two separate supplies with two separate neutrals. Okay, an isolation transformer on output is there to create a new neutral earth reference. Two separate things. So if we was to have two supplies into the UPS of a modern UPS, you would need another transformer to isolate the neutral, which is a big, heavy, inefficient, expensive option, and also not as resilient. Okay, a lot of people believe having those two supplies, one for the rectifier, one for the bypass, is a very resilient application. But having the ability to have a small ATS on the input means the UPS will transfer from one source to another with only a short time on battery, get back to normal mode. So you have that resilience as well as the cost and space and things like that. So it's a different approach to that. And we are seeing a lot of people go down the line of an ATS rather than just having two fixed supplies into the unit.
Thank you. Another question about the composition of the batteries. Somebody's asked, are nickel zinc batteries appropriate in healthcare applications?
Okay, the nickel zinc is quite a new product to the market. It is ideally suited for data centers. It is ideally suited for that very fast discharge of 5-10 minutes. Yes, you can use it. It's a very safe battery, but it's not really designed for the 3-hour battery that we see. So again, going back to it, the lead acid is actually, although old technology, is actually a very good application for the lead acid battery. So yeah, just look after it. Whatever you do, look after it. A lot of people think the lead acid battery is not reliable. It is, reliable battery if you look after it, you know. So,
yeah, I think you stressed throughout the importance of good maintenance for the batteries and the condition. Somebody else has asked, is it better to have smaller downstream protection devices or a bigger UPS to handle faults? Doesn't the extra wiring and distribution cost of smaller devices make it more expensive?
yeah, you should always go for the smaller device as possible. First thing you do, okay? A lot of people say we do in healthcare, we not in healthcare, in sort of life safety systems say, well, I always use C32s. What size UPSs do I need to trip a C32? And it's in the region of 150 to 200 kilowatts. You know, it's a big UPS. So if you can get away with a few extra circuits of 16 amp, then it's probably cheaper to do it that way than buy a big UPS. Okay, we're doing ourselves out of a sale, but that's the way you should be doing it. And we also see it in the medical, situation. IPSs often come with 20 amp circuit breakers in. You might be able to put 16 amps in and make it smaller. You know, another thing on that though is we often see a 10 kVA IPS fed by a 10 kVA UPS. Yeah. In that case, that 10 kVA UPS probably cannot trip those 20 amp, 16 amp breakers in the IPS. You're typically going to need a much bigger than a 10 kVA on a 10 kVA IPS. Okay.
Thank you. Another question. I mean, you partly answered this earlier about batteries, but somebody's asked, are there any restrictions on using lithium-ion battery systems in hospital buildings?
We haven't seen any because we personally haven't been asked to put lithium-ion in. That's proof of it. But as I would say, as I said before, I would go to the stakeholder, I'd go to an insurance company and say, what do you want, to see if we're going to put a lithium-ion battery in? But as I said, it's not the right application for a lithium battery. Yeah, the lithium batteries are good for a cyclic application. They're good for short, fast energy storage situations, but not for long-term standby application. Okay, unless obviously these guys might be talking about a different application on site for energy storage. In that case, it's typically we're going to put that in a container in a car park somewhere.
A few more questions, if you're okay for time,
yeah.
Alex.
Yeah, no problem.
Somebody else has said, if I have a generator, can I reduce the UPS battery size?
In healthcare, yes, from 3 hours down to 1 hour, if that generator is available in 15 seconds. In a non-healthcare, in a normal environment, if you like, for data centers, absolutely. I mean, the UPS autonomy only has to be long enough to bridge the gap that you need. Yeah, so we are seeing batteries quite commonly going down to 5 minutes and less in the data center market, just enough to get the generators on, and that's it. But when we have life safety, there are regulations that we have to follow for autonomy, and that's that.
Thank you. You've stressed the need for the importance of maintenance and servicing. Somebody's asked, how often does a hospital UPS need servicing, and what's actually done?
Okay. With any UPS, we have to follow the manufacturer's recommendations. HTM says to pay at least once a year, but many manufacturers will say 2 times a year. And also there is maintenance to be done by the users themselves. So we want to go in on a monthly check, make sure everything's working, make sure that the batteries will work if it's needed. But for us, when we go in and do a maintenance, we are there to ensure that the UPS does as it says it's going to do, or warn you that it's not, and this is the recommended actions to get it back up to standard. So we are going to operate the UPS, calibrate the UPS, test the UPS, and ensure that it's in absolute tip-top condition, and warn you if there's any problems coming up. So there's all UPSs have consumable items in capacitors, fans, batteries, and things like that that have to be changed as per the manufacturer's instructions, and we will be warning of those types of things coming up, and you should be aware of that from whoever's doing the load tests. Okay.
Thank you. We're all very aware, and particularly the healthcare engineering and state management community, of the imperative to reach net zero targets. So with the sort of final questions I've got are around that theme. Somebody said, do you see fuel cells replacing batteries and generators for UPS in the future?
Not in the near future. Not in the near future. Hydrogen is a problem. Storage of hydrogen is a problem. And our generators are being designed for hydrogen use and fuel cell use and things like that. It is more of a for something that's going to be used on a regular basis. UPSs for healthcare are standby. So a fuel cell isn't so much of a good as a standby as the battery as it stands. We are different technologies coming along, but at the moment, the good old lead acid battery is still a very, very good solution in this application. Yeah.
Couple more questions. Can I use a PV array to charge the UPS batteries instead of mains?
In theory, yes. But the best way of doing it is to keep things separate. The UPS is there in case you need it. It's a critical supply. So if you've got PV on your property, it's always best to have that just feeding into the input supply onto your input board of your facility. So therefore you are reducing the consumption from your mains. And if the battery is recharging, it will use the power coming from the PV rather than the mains. But then the UPS is always there as a critical backup if you need it. Okay. There are systems around that will balance between the load, especially on energy storage systems, but we have to make sure that we have the battery available when we need it in a life safety application, for sure.
Thank you. Last question here. How are UPS manufacturers addressing the need for sustainability?
Okay. Most UPS manufacturers are fighting to get the most efficient UPSs out there. That's one thing. To make sure that we can only use the amount of energy that we need to use. So we're looking at over 97% online for a lot of UPSs. So we are making sure, use as little energy as we can. The UPSs do have the eco passports. Many manufacturers are making sure we have an eco passport for the UPSs to make sure that it could be made sustainability in the factory to start with, and then it has a life cycle and recyclable part of it. I think we have to be very careful as an industry about using batteries and things like that. The lead acid battery is recyclable, 98%. So it's a very good recyclable battery. More of a personal thing, we have to be very careful with lithium ion because that is not being recycled properly at the moment, and there's a lot of work to be done in that recycling of these lithium batteries, but also making sure we look after these UPSs. If we can stretch out the lifespan of the battery of the UPS, we're not going to be throwing it away and buying another one. If we can make that battery last 10 years instead of 6 years by looking after it properly, then we are doing our bit for sustainability. It's likewise with the UPS. A UPS will last 10 to 15 years comfortably if it's looked after. Put it in a poor environment, it might only last 5. Well, I think that's the biggest thing about sustainability is looking after the equipment we've got rather than just throwing it away and buying another one.
Thanks, Alex. That's a very clear message. Well, that takes us to the end of the many audience questions we have. In addition to the questions, I had a number of very positive comments about how interesting a presentation and how well structured the webinar was. So thank you very much to Alex Ems here of Kohler UPS, and thank you very much to all those who attended the webinar today. And in answer to the question, a copy of the webinar will be circulated, so you will be able to refer to the presentation later, anybody who attended. Thank you, Alex, and thank you to all the attendees on this HEJ and Kohler UPS webinar.
Okay, thank you and
Thanks.
goodbye. Thank you.
Goodbye.